Let us start lecture 27, and the course is phase diagrams in single component and binary systems. For the last few lectures, we have been discussing a mixture of gases, and that too ideal gases. And we have tried to understand after mixing of those ideal gases, what could be the free energy after mixing, or we call it del G mix. Here we are trying to calculate Gibbs free energy, and then subsequently we have seen what will be the effect on enthalpy of mixing as well as entropy of mixing. And we have seen that enthalpy of mixing becomes 0 when we mix several ideal gases, and also we have seen that entropy of mixing as well as Gibbs free energy of mixing, they are related to the mole fraction of those gases, all those gas components in a mixture, and we have found out a relation between del G mix and mole fraction as well as del S mix and mole fraction. So, today we will extend that particular concept, and we will now talk about a condensed solution. In fact, when we talk about gas mixtures, that is also forming a homogeneous gas mixture, since we are considering ideal gases, since they do not have all those molecules or atoms of ideal gases, they do not interact with each other. So, that is what they are actually forming random solution and homogeneous solution, what is basically considered as a mixture. Now, in case of condensed system, situation would be little different. Okay. So, that we will be treating now the condensed system. So, that is condensed mix or condensed solution. Okay. So, today's topic will be condensed solution and its mixing Gibbs free energy. These will be needed, these information or these concepts will be needed in order to derive equations which will allow us to give rise to phase diagrams in binary systems. So, initially we will start with multi-component and of course, more than 2 components, and then we will actually confine our discussion on binary systems. We will be having 2 components A and B and try to see what will be the mixing free energy, and consequently what will be the mixing enthalpy or mixing entropy, as well as now we will try to calculate the mixing molar volume after we mix A and B. Okay. So, let us treat that. Now, in fact, what we have seen in case of ideal gas mixture, okay, at a particular temperature and pressure. Of course, here we are considering closed system and fixed, which means that it is a fixed composition. Also, we take that particular option because it is ideal gas mixture, there will be no reaction or interaction. So, in that case we have found delta J mix equal to okay. So, here Xi is the mole fraction of ith component and Ni is the mole number of mole of ith component in the mixture. R of course universal gas constant, T is the temperature where we are operating. This was the equation we found out, and we have also seen that this will be always negative when it is a mixture, because Xi is less than 1. So, that is what ln Xi term would be negative. So, mixing of ideal gases will be always a spontaneous process, fine, and consequently we have found out del H mix equal to 0. So, that means enthalpy evolution due to mixing of ideal gases will be nil, And then we have also found out del S mix equal to minus Ni R ln Xi. Okay. So, that is what we have found out. So, this would be always positive since ln Xi is negative and there is a negative term, negative sign. So, it becomes, and of course, it will be, there will be a summation because we are considering number of gases in a mixture. So, these we have found out. In fact, we can also say that G of mix can be written as Ni Gi bar. So, this is basically, if we extend it, we can write it as N1 G1 bar plus N2 G2 bar N3 G3 bar, like this, where G bar is nothing but, and of course, if I put I, this is partial molar Gibbs free energy of ith component in the gas mixture. And when we can write? When T and P are constant. So, then we can write this way. In fact, this is basically nothing but Gibbs-Duhem equation, one of those Gibbs-Duhem equations. Now, if we try to find out all those partial quantities can also be termed as chemical potential of that component in that particular mixture or homogeneous mixture. So, now if we take, there is a binary system. So, let us say there are A and B gases, okay, A and B. Let us say Na is basically number of mole of A and Nb is the number of mole of B which are mixed, okay. And that time, and in fact, this quantity is basically total free energy, of course, gives free energy of the mixture. So, this one is the total Gibbs free energy. Let me just, you put it, the Gibbs is, of course, G is of course Gibbs free energy. So, that is what I am not writing all the time. Now, these are the number of moles of A and B respectively, and when we mix them, then I can write, or I can write G prime equal to Na Ga bar plus Nb Gb bar, we can write that. Now, if I differentiate this one, so G mix, which can be termed as G prime equal to Na Ga bar plus Nb Gb bar. So, if we, and this is basically for total free energy of the mixture. So, then I can write, if we differentiate, it be equal to Na we can write this. So, if we now let us look at the Gibbs-Duhem equations. At constant temperature P, if they are constant in a closed system, that case we can write this way, and if we take binary system, we can write this, then we can write G equal to and then we can write one more equation we have derived before. So, it is equal to 0. Okay. Now, if we take this, so then we are seeing that this one and this one, these two terms, if we add up, then it should yield 0. So, it yields me, so it's me this. Okay. Now, this is for total. Remember that this is total free energy. Now, a similar way, if we take this one again, okay, if we take this one again, so in fact we can find out G prime if I divide it by Na plus Nb, then this becomes G, which is let us say Gm molar Gibbs free energy of the solution. Means this is for 1 mole of solution, because we are dividing it by the total mole, since it Na and Nb are the number of moles of A and B components. So, that is what it becomes, the total mole. This is the total mole. So, if we divide G prime with this one, then it gives me molar Gibbs free energy. It can be given as Na plus Nb Ga bar plus Nb Gb bar. So, then this can be written as Gm equal to this quantity would become Xa, this quantity would become Xb, which are the mole fraction of A and B. So, Xa Ga prime bar plus Xb Gb bar. Okay. So, now once we get this, then the same thing can be drawn here. The same thing I can write this way. I can write this. So, once we write this, so let us say this equation 1 and let us say this is equation 2, I can find a relation between dxa and dxb. I can actually see Xa plus Xb equal to 1, then dxa should be equal to minus dxb. So, once we know this, then I can write this equation as delta Gm equal to Ga I can write this, I can replace dxb with minus dxa. So, once we write that, this is let us say equation 3, and from this we can write this is equation 4. Now, we see equation 1 and equation 4. Now, if I add equation 1 plus Xb into equation 4, let us see what happens. So, Gm equal to fine, and then we get Xb would be equal to we get this. So, if we add up, then these two would get cancelled. So, finally, we get Gm plus Xb Xa equal to, or Xa plus Xb Ga bar. So, this gives us GA. So, because this is equal to 1, so GA bar would be equal to GM plus XB okay. So, this is one equation we draw. Now, another equation can be drawn if we take equation 3, let us take equation 3 or rather equation 2, let us treat that also. Equation 3, this is one equation, this is let us say equation 5 and let us treat equation 3 rather equation 2, which gives me dGm equal to GA bar okay. So, now if I use this same replacement same treatment here, instead of dXA I will replace instead of XB dXB I will replace dXA, then let us see what happens. So, now I can replace it equal to minus plus GB dXB. So, here I have replaced dXA with minus dXB. So, then again I can treat this way. Okay. So, let us say this is equation 6. Now, let us take equation 1 plus XA into equation 6. Let us see what happens there. So, we get GM equal to XA GA bar plus XB GB bar, and then here we get XA minus XA plus XA, fine. So, if we add them, then we can see that GM plus XA would be equal to, this would get cancelled. So, XA XB plus XA, this one should be B, this. Okay. So, now this quantity is equal to 1 for binary system. So, then we get bar equal to GB bar equal to GM plus XA dGm by dXB. So, this is equation let us say 7. Now, we have two equations, one is 5 and 7. So, these two equations are actually indicating that the partial molar quantity, this one and this one for A and B components in a mixture at a temperature and pressure, when these two quantities are constant temperature and pressure, that can be found out with reference to the molar free energy of the solution, as well as the composition at which we are trying to calculate that partial quantity, and the slope of GM plot, GM the mixture that molar free energy of the solution, when we plot it with reference to composition at constant pressure and temperature, it will show a curve actually. So, we will see later. So, at any point, that means at any composition, when we try to find out the partial molar quantities of A and B, that can be found out from these two equations, and where we only need this value, molar free energy of the solution, and the slope at that composition for that molar free energy of the solution plot with composition, and respective compositions of A and B. So, these two equations will be used when we try to calculate binary phase diagrams. So, this is actually done with reference to ideal gas mixture, but this can be extended for the condensed phase also. Okay. So, at least we could see that how to calculate partial molar quantities from molar free energy of the solution or the mixture, and the slope of that molar free energy plot at a particular composition. Okay. So, these two equations will be very important, and you will see the use of these two equations later. So, let me stop here. We will continue our discussion on this particular topic, and now we will bring in the condensed solution, which will be either solid solution or liquid solution. And there also you will see that these two formulas will be operative. Let me stop here. Thank you very much.